The first method I'm going to give is generating functions, and essentially that's using generating functions to solve or to obtain the solutions of recurrence relations. And by recurrence relations here, let me remind you, I refer to linear and constant coefficient recurrence relations in general. So it can be homogeneous or non-homogeneous, but we will only look at linear and constant coefficient recurrence relations. So first of all, let's remember the definition of a formal generating function, and the sequence that will give rise to the generating function in this case is our t sub n for n greater than or equal to 0. So the formal generating function is defined as the sum here for n greater than or equal to 0, tn times x to power n. So for any sequence, if you remember, you can define a generating function. And in this case, our generating function is of the form, let me put it here, t0 times x to power 0 plus t1 x to power 1 plus t2 x to power 2 plus t3 x to power 3 dot dot dot. Okay, it's an infinite sum, and this is the function. And remember our discussion about generating functions. We do not care about the value of the generating function, right? We just care about the coefficients, because the coefficients are what describes the sequence. And in this case, we are going to be more interested in the coefficient of the term x to the power n, because that will give me the general case of my sequence Tn for a general n. Okay, so given a recurrence relation, if I can come up with an expression that provides me the coefficient of x to power n in the generating function, then that will give me the solution. So let's see this on a simple example, how we can use generating functions to obtain the solutions to recurrence relations. To find the solution of a recurrence relation, we can obtain the coefficient of x to power n in its generating function. For instance, try to solve the recurrence relation Tn equals Tn minus 1 plus 3 to power n for n greater than or equal to 0. Well, in this case, this should be maybe n greater than or equal to 1, because, well, this here is going to be T0 for n equals 1. But we are not going to look at negative indexes, so we can start n from 1. And we are also given the initial condition t0 equals 1. Okay, now the trick here is to try to write each side in terms of the generating function. So to be able to do that, well, we are given this. First of all, observe that, yes, this is a linear recurrence relation. It has constant coefficients. It's not homogeneous because we have the function 3 to power n, and the degree of this recurrence relation is 1. Okay, so it fits our bill. So let's try to come up with the solution. And as I said, we would like to express both sides of this equality in terms of the generating function. So to be able to do that, I'm going to multiply each side by the term x to power n, and I'm going to apply an infinite sum to both sides. So Tn equals Tn minus 1 plus 3 to n. Multiply both sides by x to power n. What you get is Tn times x to power n equals Tn minus 1 times x to n plus 3 to n times x to n. Now, at this point, I'm going to apply an infinite sum to both sides, but I need to be careful about the limits. You see, this one starting from Tn minus 1, therefore, I should apply my infinite sum, yes, up to infinity, but the initial index should start not from 0, but from 1. Because in this context, t minus 1 is not defined. We are interested in Tn and greater than or equal to 0. Okay, so look for the smallest index, which is n minus 1 in this specific example, and make it 0. Okay, so start the summation from 1 to infinity. Okay, so my generating function definition is here. Of course, the sum starts from 0, obviously. Therefore, this term here is equal to the generating function except for one term. It's just missing a single term. That is for n equals 0. Okay, so that is equal to, therefore, this left-hand side is equal to the generating function minus the term for n equals 0, which is t0 times x to the power 0, which is just t0. And on the right-hand side, what you have is this sum for n greater than or equal to 1, tn minus 1 times x to n. Now I can write this as n greater than or equal to 0 of tn times x to n plus 1. It's the same summation because if you actually expand this, it will be t0 times x plus t1 times x squared plus t2 times x cubed plus t3 times x to the power 4 and so on. Therefore, I can write this as starting from 0 up to infinity, tn times x to n plus 1. So if I pull one of the x's here to outside of this sum, because it doesn't depend on n, obviously, what I have here is exactly the generating function. This here, okay? So this is x times the generating function. And finally, this term here, well, 3 to the power n, x to the power n, that's 3x to the power n. That is n from 1 to infinity. Again, be careful with the summation limit. Now, if I had this starting from 0, this would be 1 over 1 minus 3x, right? Because if you remember, summation from I equals 0 to infinity, some number, let me call this y, to power I is equal to 1 over y, 1 minus y. Provided that y is in magnitude less than 1, but here, that's not our concern. If you remember, the convergence properties of the sums here is not our concern. Therefore, my summation here is missing only one term again. If I had started this from 0, that would have been 1 over 1 minus 3x. So if I subtract the term for n equals 0, which is 3x to power 0, I get this. Okay, so what I have here is now I have the generating function here, x times the generating function here. If I put this on the left-hand side, I have 1 minus x times the generating function, and I switch this to the right-hand side, so I get t0 as this term here, and this here, well, t0 is 1 because that is given to us as the initial condition, and this here is the result of this sum. Okay, so what is the next step? Next step is, well, this generating function, well, this is 1 and this is also 1. These cancel these out. So the generating function is equal to 1 over 1 minus 3x times 1 minus x. So essentially, we actually have found the generating function, and what remains to be done is to find the coefficient of the term x to power n in this function. Now, obviously, what you can do here is, for instance, if you have access to a computer with an internet connection, you can go to Wolfram Alpha and try to factor this out as a Taylor series expansion. In that way, maybe you can come up with the coefficient of x to power n. But obviously, that may not be possible always. And also, we also want to have an analytical approach to such problems. So if you have the generating function, what is the method to obtain the coefficient for x to n? and thus what is the method to obtain the solution to the recurrence relation. So when you have such a function, this is a rational function. A rational function essentially is a ratio of polynomials. Okay, so in the numerator I have 1, which is a polynomial. In the denominator I have 1 minus 3x times 1 minus x. The good thing about this is it's already factored out. So I can apply a partial fraction expansion here. So the factors are already known, 1 minus 3x and 1 minus x. What I just need to find is this a and this b coefficients. So if you equalize the denominators, you have a times 1 minus x plus b times 1 minus 3x divided by their product, and organize the terms so that you have the constant here and the coefficient for the x term here. This should be equal to this entire thing. So a plus b plus minus a minus 3b times x equals 1. Okay? And I can write it here, a plus b equals 1, and minus a minus 3b equals 0, because I don't have an x term here. If this were like 1 plus 2x, then this would have been 2, but that is not the case, obviously, here. Therefore, it should be 0. Okay, so solve these simple system of equations with two unknowns. You obtain the values of a and b, which turn out to be 3 over 2 and minus 1 over 2. Therefore, my generating function is given as 3 over 2 over 1 minus 3x plus minus 1 half over 1 minus x. So what is the next step? Now, when you have this in this form, it's easier to express these as generating functions in some form, right? This I can write, well, that is simply because, remember, I from 0 to infinity, y to I is simply 1 over 1 minus y. So, for instance, when I have 1 over 1 minus 3x, this I can write simply as I from 0 to infinity of 3x to power I. Simple as that. Okay? Therefore, 3 over 2 over 1 minus 3x is equal to 3 over 2, the sum from 0 to infinity, 3x to power n, minus, coming from this minus sign, 1 half, the sum n from 0 to infinity, x to power n, because this is simply 1 minus x. And this whole thing is my generating function, which is by definition equal to this. Now, when you look at the left-hand side and the right-hand side, you just equate the terms with x to power n, right? On the right-hand side, that would be the x to power n term is going to be 3 over 2 times 3 to the power n, because this would be 3 to the power n times x to the power n. And then you have minus 1 half times 1, because that's simply x to the power n. Therefore, Tn, the coefficient of xn on the left-hand side, equals simply 3 over 2 times 3 to the power n minus 1 half. And this is the solution for the recurrence relation given here. Tn equals Tn minus 1 plus 3 to the power n with the initial condition T0 equals 1. The solution is 3 over 2 times 3 to the power n minus 1 half. Now, obviously, if you change this function or the coefficient here or the initial condition, the solution is going to be different.